Welcome to the lecture series on data structures. In this lecture, we talk about AVL trees. In the previous lecture, we talked about binary search trees, and we observed that, one of the drawbacks of binary search trees is that they may get left skewed or right skewed at some times. The question is how to avoid that skewness. In 1962, Adelson, Welsky, and Landis has proposed in their work a mechanism to reorient the trees whenever there is skewness, to reorient the trees. In their work, they proposed a factor called balance factor, which can be identified at every stage of every insertion or deletion of the vertex, and whenever there is a change in the balance factor, immediately we can reorient the tree. So in the AVL trees, the insertion is and deletion will change the orientation of the tree, whereas retrieval of the data from the AVL tree is same as the binary search tree. There is no change in that, same as it is with the binary search tree. Now, when a node is inserted into the binary search tree, then the balance factor may be altered. So when it is tending to create an imbalance in the tree, then immediately we can reorient the tree. Similarly, on deletion also, deletion of the vertex may also create imbalance, and once there is an imbalance, we reorient the tree in such a way that the balance is established. In the subsequent slides, we will see how this can be achieved. Now we look into the notations of AVL trees. First, we define height of a tree. Height of a null tree is taken as -1, height of a single node, tree having single node, as 0. And then height of a node is length of the longest path from the node to a leaf node. A binary search tree is said to be an AVL balanced tree rather, if the difference between the heights of the left subtree and right subtree is at most 1. And both subtrees are themselves are AVL trees. So this can be defined as a balance factor, of course. The balance factor of a node U is the difference between HL of U minus HR of U. Height of left tree minus height of right subtree. And in the AVL tree, every node has a balance factor of 0 or -1 or +1. These are all alternative definitions of AVL trees. Here we'll look into an example here. The tree has several vertices and balance factors are depicted in brackets. If you observe the last nodes or the leaf nodes, all of them have balance factors of 0 because there is no left and right children for them. For the vertex 7, the left subtree has 2 edges, whereas the right subtree, the length of the longest path in the right subtree is 4, 7, 17, and 9, 12, and 16. So 4 edges are there. So the difference between the lengths between left and right subtrees is 2 minus 4. So -2 is the difference. So balance factor is -2. And if you observe for the node 20, the length of the longest path in the left subtree is 27, 17, 8, 12, 16. 1, 2, 3, 4, 5 edges are there in the left subtree. Whereas in the right subtree, 2 edges are there. So 5 minus 2, 3 is the balance factor for node 20. So clearly we can observe that there are 2 nodes, 7 and 30, of course 3 nodes, and 12 are not balanced. All the remaining nodes are in balance, but these 3 are not balanced. So it's not an AVL tree. So in AVL tree, every node should have balance factor between -1, 0, or 1 only. On insertion of a node in a binary search tree, or in an AVL tree rather, if it is an AVL tree, all the nodes are already balanced. If we insert a node at any location, then it may cause an imbalance. This imbalance can be observed in 4 ways. We may insert the node in the left subtree or right subtree of a node. Now, let V be a node that is inserted and that resulted in an imbalance at a node A. That means if I add a vertex V, and after adding the vertex V, if we recalculate the balance factors, let A be the latest the smallest ancestor of V that had lost its balance factor. then A is such a vertex, let us take. Then there are four types of cases may arise. That is, the balance of A is lost on insertion of a vertex V either in the left subtree of A. There is LL rotation, that is called LL rotation. Node V is inserted in the left subtree of A, or vertex V is added in the right subtree of A, that is LR rotation, and V is inserted in the right subtree of A, that is RR rotation, and the vertex V is added in the left subtree of A. So whenever V is added in any one of these cases, A may lose its balance factor. Now, if this is the case, we need to achieve the balance. How to achieve the balance, we'll see later. Now we see the first scenario, LL rotation, where node V is inserted in the left subtree of A. If you look at the leftmost tree scenario, vertex A has balance factors +1. B is a vertex which is in the left child of A, and for B there are two subtrees, left subtree of B, BL, and right subtree of BR as right subtree. And let us assume the heights of the left and right subtrees of B as H. Let H be the height. And the height of AR, the right subtree of A, is also taken as H. Then if we calculate the balance factors, since at B, the length of the longest path from the left subtree is H plus 1, and length of the longest path at right subtree is H plus 1, so balance factor is 0. Similarly, at A, the length of the longest path is H plus 2, whereas the length of the longest path in the right subtree is A plus 1, so the balance factor is plus 1. At this point of time, there is no imbalance, everything is good, so it's an AVL tree. Now, if come to the middle diagram, if vertex V is added in the left subtree of B, so that is added to the left subtree of BL. Now, if we recalculate the balance factors, since V is added in the left subtree of BL, the balance factor at B now changed to plus 1 because the length of the longest path now has changed to H plus 2 because one length is added, H plus 2, and the right subtree has H plus 1, so balance factor is plus 1. Now when it comes to the balance factor at A, it is H plus 1 plus 1 plus 2, H plus 2 and H plus 3 rather, and the right subtree has height H. So the balance factor at A is plus 2, which is an imbalance. Previously it is in balanced state. Because of addition of vertex V, it is balance is lost. Now again at A, the balance factor is plus 2 because the length of the longest path has changed. The length of the longest path here is H plus 1, H plus 2, H plus 3. And the right subtree is H plus 1. Now, if we observe, one more observation is the keys of the left subtree of BL is always, now all the keys in the left subtree BL is less than key of B, and key of B is always less than keys of BR, and which is less than key of A, and which is less than keys of AR. This is the property of binary search tree, of course. This has to be maintained throughout. Even to achieve the balance, we need to keep this in mind. Now, how to get the balance is simply right rotate. Simply we rotate the vertices right side and we push B upward and A downward as the left child of B, right child of B. So if you push B upwards and A as right child of B, the scenario here is B has left subtree and right subtree, BL and BR. BL can be still with the left subtree of B, but since we have added A as the right subtree of B, we need to take care of BR. But according to the observation of on keys, all the keys of BR are less than A but greater than B. So all the keys should be on the right side of B but left side of A. So simply attach the left subtree BL as the left subtree of A, so that the comparison of keys is still maintained. So push B upwards, push A downwards, and attach the right subtree BR as left subtree of A. By doing this, we can achieve the balance. If we recalculate the balance factors again, we can clearly observe that balance factor of B is 0 and the heights are adjusted here. So balance factor of B is 0 and balance factor of A is 0. Now we will look into the example here by following the above observations. 15, 10, 7, 12 and 20, the balance factors are calculated, and vertex 5 is added in the left subtree of 15. 15 has lost its balance. So we push 10 upwards, we take 15 as the child of right child of 10, and then the right subtree of 10 is taken as the left subtree of 15 as added. So like this, again if we calculate the balance factors, balance is achieved. Now we look into another scenario where LR rotation, where node V is inserted into the right subtree of left subtree of A. Again, if you observe, A is a vertex initially having +1. Now we can observe clearly observe the heights easily. A has vertex balance factors +1, B is a left child of A, and BL is a left subtree of B. AR is the right subtree of A, and C is right child of B. Now C has left and right subtrees CL and CR. Now let us assume that the heights of CL and CR are h-1, whereas heights of left subtree of B as h, height of right subtree of A as h. At this point of time, C has balance factor 0 because both subtrees are same height, and at B also balance factor 0, at A balance factor is +1. Now if I add a vertex V on the right subtree of left subtree of A, so B is on the left subtree of A and C is the right subtree of left subtree of A. So we are adding a vertex in the right subtree of left subtree of A. If that vertex is added and recalculate the balance factors, now C has a balance factor of +1 because length has increased in the left subtree, +1, and again at B, since vertex is added in the right subtree, balance factor is -1, whereas at A the balance factor is +2. Because CL has height h-1, one more vertex is added h, then h+1, h+2, h+3 is the length of the longest path, whereas h+1 is the right subtree height, so +2 is the balance factor. So A is a vertex which has lost its balance because of addition of a vertex V in the right subtree of left subtree of A. Now how do we achieve this balance is we push C upwards and we push A downwards. Again, to do this, the important observation here is keys, comparison of keys again. Just like in the previous slide, compare the keys on left subtree BL should be less than keys of B, which are less than keys of CL, less than C, keys of CR, then less than keys of A, then keys of AR. This balance has to be maintained throughout. By keeping this in mind, we can rotate the tree in such a way that we push C upwards and A downwards. A is the right child of C. Since C has left and right subtrees and both the trees are disturbed now, by observing the comparisons, CL, the left subtree of C, can be right subtree of B, and right subtree of C can be left subtree of A, so that the comparison of keys is still maintained. So by doing this, we can recalculate the balance factors. At B, the balance factor is maintained because CL has height h-1, one more vertex is added, h+1 is height. BL has height h+1, so balance factor is 0. Similarly, at A, now the balance factor is -1 and C balance factor is 0. So this balance is achieved. We can observe here in the example, in the bottom example, vertex 14 is added in the right subtree of left subtree of 20, and because of addition, the balance factor of 20 is lost. So it has become -2. So what we're doing, we're pushing 18 upwards, making 20 as the right child of 20, and the left subtree of 18 is 16, 14 that is added as a left subtree of 12, and the right subtree of 18 is added as left child of 20. So similar procedure we can adopt, and we recalculate the balance factors. It can be observed they are achieved. Balance is achieved. Now we look into the RR rotation, where the vertex is added in the right subtree of A, and because of addition, the vertex A has lost its balance factor. In this case, A is the vertex having left subtree as AL and right subtree as starts with B. B has left subtree as BL and right subtree as BR. And here we assume that lengths of AL is H, and length of BL and BR are H. And if we calculate the balance factor at B, BL having height H, so left and right subtree is H plus 1 and H plus 1, balance factor 0. And at A, the balance factor is left side is H plus 1, right side is H plus 2, so balance factor is minus 1. Now, if a vertex V is added and the right subtree of B, BR, so that it is added in the right subtree of A. And if we recalculate the balance factors at B, the length of the left subtree is H plus 1, length of the right subtree is H plus 1, H plus 2. So balance factor is minus 1. Whereas at H, the balance factor left subtree is having height H plus 1, whereas the right subtree is having H plus 3. So balance factor is minus 2. So balance is lost at A. Now, how do we achieve the balance? We left rotate the tree. Simply push B upwards and A as left child of B. Again, observation on the comparison of the keys is crucial here. By following that only, we have to rotate. So push B upwards, make A as a left child of B, so that AL is a left child. When we push B, the left subtree of B, BL, shall be made as the right subtree of A, and BR will remain there itself, and vertex V there itself. By doing this, again, if we calculate the balance factors, at A, the balance factor is 0 because same heights are there, and at B, balance factor is again 0, balanced on both sides. Now we look into the example here. 20, 10, 30 and 25 and 35 balances are calculated. 45 is added to right child of 35. So, and if we recalculate the balance factors, balance factor 20 is lost. Again, we apply the left rotation on this. 30 is pushed upwards, 20 downwards, so that and if we recalculate the balance factors, balance is achieved. Now we look into the last one, fourth rotation, RL rotation. That means when vertex is added, V is added in the left subtree of right subtree of A. So in this case, again, we'll consider the observation here. A is a vertex, B is right child of A, and C is left child of B, and CL and CR are the left and right subtrees of C. Let us assume that the heights of left subtree of A, AL is equal to H, whereas the left and right subtrees of C as H minus 1. And we right subtree of B is also BR is having height H. Now in this case, if we calculate the balance factors, the balance factor of C is 0 because they are balanced. CL and CR are H minus 1 and H plus H and H are the balance factors. Whereas the balance factor of B is 0 again, and balance factor of A is minus 1. Now if we add a vertex B as a right child of CR, then the balance factors of C is minus 1, you can readily calculate. Balance factor of B is plus 1, and balance factor of A is lost as minus 2. Now how do we achieve the balance here again? We need to push C upwards and make A as a left child of C, and CL and CR are the left and right subtrees of C. CL is made as the right subtree of A, and CR is made as a left subtree of B. So that again, if we calculate the balance factors, balance is achieved. Now if you look into the examples here, 35 is added as the right child of 30. 30 is the left child of 40, and 40 is the right child of 20. So 35 is added in the right subtree of left subtree of 20, and addition of which 20 has lost balance. So we push 30 upwards, make 20 as a left child of that, and there is no left subtree of 30, so we add the right subtree of 30 as the right subtree of 40 only. So this is how we can achieve the balance.